Yeah, okay. So thank you for the nice introduction. And as Caroline already said, the first talk is about the modeling of micropollutants in a strongly regulated cross-border lowland catchment, and especially the challenges that comes along when trying to do so. And as I'm the first of 3 talks today, which are all more or less linked together, I will give a short introduction of the general problem, and maybe some of the points that I raised in my talk will be answered in the other 2 talks. So to start with, I want to give a short introduction of what the general problem of micropollutants in our surface waters is. So this general problem can be framed in one particular sentence, that chemical substances, for example, metals, fertilizers, pharmaceuticals, and plastics are detected in large quantities in rivers all over the world. And this sentence can be structured in 3 major points, which the result of is a sentence, where the first one is that around the world we have around 150,000 substances that are washed into the environment worldwide through the production of goods, and that these substances in sewage plants, treatment plants, only partly, so not completely, are degraded and retained. So therefore these substances get into the water bodies and in the groundwater, and some of them possibly even into our drinking water. And third, not all of these substances can be broken down by nature into harmless end products. So for some of them, it's possible, for example, via photolysis or hydrolysis, to be transformed and converted into harmless end products. But for most of them, this can only be done partially, and some of them cannot be done. So these are the persistent substances. And so we have a general problem of pharmaceuticals or chemical substances coming into our water cycle. And when in the water cycle, from time to time in media, you can see headlines like this one, which I have from the Daily Mail, where they mention the problem of female birth hormones to make fish populations mostly female. So the problem is that when these hormones are in the water, the fish stocks go through a kind of feminization, where the water is polluted with female hormones and the offspring of the fish usually becomes mostly female, which leads to the long-term extinction of the total population. And this is only the effect of one of the substances, and as there are many thousand substances in our waters, you can easily imagine that there are many, many undesirable effects that can occur in the biolife. And when talking about the biolife, this is not a one way, so there might be the way back to us as humans and to other wildlife. So there's a very famous example of vulture populations, and these vultures eat the corpses of cows, but also fish. And if the fish or the cows had contact with diclofenac, the cows via treatment, and the fish because they were in water that was polluted with diclofenac, which is a painkiller, these vultures eat the meat, and the meat is with diclofenac, and then the birds die because birds are highly allergic to diclofenac, and this can lead to the total extinction of populations, as it has been observed in India and Spain in the early 2000s. And you can easily imagine that all these substances not only have an undesirable effect for animals, but also for us. So when we humans are in contact with water, because we drink it, but also when we are in nature and we go swimming or water sports and so on, and we come in contact with all of these substances, this can be highly undesirable for us. And this is why we all should have an interest for as clean as possible waters. And now the question may arise, because I will talk today about modeling, on how models can help with this problem. And in general, it can be said that thousands of these substances can be detected analytically in laboratories today, but Measurement data can only provide temporarily and specially limited information, because when you go out there and you take grab samples, you get information about concentrations, but only at a given time, at a given place. And a river or basin-wide or even national monitoring of all waters via monitoring is very complex to manage and very, very expensive to do. So risk assessment for hundreds of known dangerous substances and thousands of potentially harmful substances in an entire river basin or world, national-wide, only via monitoring is basically impossible to do. And this is where models can help. So the model that I use and the model that we use in the at the Osnabrück University is the so-called GREATER model, where GREATER is an acronym for Georeference Regional Exposure Assessment Tool for European rivers. And the GREATER model combines a GIS with FATE models to consider the overlying effects of multiple emissions, where the current version, GREATER 4.1, is implemented as add-in for ArcGIS desktop version 10.5. The general model approach, and I cannot go into so much detail because I'm limited in time, but the general model approach is that we use a real river network of the whole watershed. So in our case, the Vecht catchment, and then we consider local emissions from all known sources. This is mostly treatment plants, but can also be, for example, industry or hospitals or agriculture. This depends on the substance that you want to simulate in your model. And then we have a mass balance for each river segment, and we simulate specially resolved concentrations, assuming steady state conditions. This is important. I will show it on the next slide because there are some restrictions coming along with this. And in the end of our model, we have a representation of the results in a map, color-coded map. So this is georeferenced. The restriction, which I already mentioned, is the steady state assumption that we have in our model, because this requires more or less constant emissions that we have to look in our model. This means that we have to build or calculate annual averages. So when looking at the emissions from treatment plants, we calculate an annual average. This means that we are not able to model temporal dynamic events like sewage overflows, for example, and other specificities. And this will be important later on when looking at the Vecht catchment. To give you an overview about the Vecht catchment that I'm now talking about and that the whole MEDUWA project is focusing on, the Vecht is a 182-kilometer long river, which has its source near Münster in the Münsterland. And then it flows from North Rhine-Westphalia in Germany to Lower Saxony, where it crosses near Nordhorn, the Vechtesee, and then near Hardenberg it crosses the border. It flows from to Zwolle, and in Zwolle it goes into the Zwarte Water, and from there in the Eiselmeer. You can also see the location in the right of the map where it's located in Germany and the Netherlands. Population density, there are more people living on the Dutch side of the catchment, as the biggest cities, for example, are Enschede, Zwolle and Emm, with above 100,000 inhabitants. And in Germany, we have only small cities like Nordhorn and Steinfurt, and in total 1.5 million people living in the catchment. And when looking at the catchment and running simulations, we are, of course, not only looking at the Vecht, but there are many tributaries, small creeks, canals, and so on in the catchment. And all of these river parts have to be taken into account when trying to run a model and to simulate. So, as you can see, we have 5 different authorities in charge, which are the Waterschapps of Drenz-Rohrische Eichel Delta, Vechtstrom, and Rhine-and-Isel, and in Germany, the authorities from Lower Saxony and North Rhine-Westphalia. And the first step that I had to do when setting up the model is to create a hydrological network out of these input data. So I worked together with all of the water authorities, gathered the data, and as you can see, the level of detail is quite different from authority to authority. So I had to build a hydrological network by reducing and merging it together and to create the one that you can see on the right side. So as a first step, mathematically and with GIS, I created my own hydrological network of the Vecht catchment. And then normally I would run simulations on Grader. So the output of the Grader model, as I said, is a georeference map. And normally you get something like here, where you get a color-coded map and you can easily identify hotspots, for example, because concentrations are mapped from green to red, where red are the highest concentrations to be found. In the map, you have, for example, in this case, the treatment plants as emission sources, which are the dots. And then you can easily use this map and go into further detail and start analytics on concentrations. But in the case of the Vecht catchment, it's not that easy because we have a highly anthropogenic influenced catchment where things are not normally behaving. This means two different things. So first, we have lots of canals in the catchment, especially in the Netherlands. As you can see with all the names on the right side, we have big canals like the Twente Canal, for example. And in total, we have 30% canal-like structures, where, for example, the Mapladip, which is written in brackets, we have some rivers where this is hard to make a difference if this is still a river or already a canal, because they are so artificial that it's hard to call them rivers anymore. And when I mark them in the map in light blue, you can see how many canal structures we have. And this means that we have to handle these canals different because, for example, in canals, the flow velocity is far lower than in a normal river. So this has to be taken into account. But then we have a fact which is far more important than this. And this is the pumping activities that goes on in the catchment. So when looking at the catchment, and this is still my hydrological network, we have an inlet, so a pump near Suften, where pumps, when running, pump ISIL water into the catchment. So in summer days, for example, when water is very low in the system, there's a need of additional water in the catchment because water from the Vecht network is used for irrigation of fields, for example. And in the Vecht, we have navigation, tourist navigation, and so on, nature conservation, for example. So there's a need of a certain water level that needs to be minimum there, and we have an additional need of water for irrigation. So Dutch authorities, when this is the case, use this pump to pump water into the water network.
Volker, it's 2 more minutes.
Yeah, then we have an additional pump in Enschede to prevent the city from being flooded, which means when pumping from both sides that physically water has only one way to go, which is up through the Zijkanal Anelo, and then the water goes from the De Handel Canal into the Vecht, and there it goes through the Vecht to Zwolle and then into the Zwaardewater. And during this path, the flow directions, of course, of canals are changed because the Twente Canal, for example, would be normally an outlet of the catchment, but now it's an inlet. And during this flow path, we have areas in the catchment where irrigation took place. So we have outlet of the Vechte into these irrigation areas. And this is a problem because, as I said, the Grader model normally has to build annual averages. And obviously, this is not possible for the Vecht. So we had to think about how could we handle this. And we handled this by setting up 2 scenarios, where one is a dry summer scenario and one is an average scenario, where the dry summer scenario is applicable for periods without rainfall between March and October, and the other one is for humid periods throughout the whole year where no pumping is needed. And as you can see, the dry summer scenario applies for 120 days a year between March and October, and the other 240 days we have the average condition scenario. So when looking at the catchment, you see on the left side a map. So we have 120 pumping days a year, and during these days, we introduce additional loads into the catchment. This means that additional load comes there through the Twente Canal, and then because of irrigation, we have a redistribution of emissions, which means that the stretches that are now colored in purple are additionally affected now. So 15% of the river network is now additionally affected with emissions, which means that 412 kilometers of river length are additional affected. When looking at the loads in this map, and this is my last slide, you can see a comparison between our dry summer scenario and the average scenario, where red marks are now have more loads than the other, and green have lower loads. And you can basically see 5 major differences that we take into account in our model. This is the first. Additional loads enter the catchment through the Twente Canal. Then pumps in Enschede are still running, so we have no change in the Enschede harbor and the first stretch of the Twente Canal. Then we have less loads in the Vecht on pumping days, which is caused because water and loads are removed from the network due to irrigation and we have a redistribution of emissions because water is pumped into the other canals, for example, the Meppler Diep, the Dedemsvaart, and the Overijssel Canal. And because of this, loads in the Vecht are less. But it is important to mention that less load doesn't mean less concentration, because in summer we have in general less water in the system. So even because we have less load in the system, the concentrations in the Vecht are still higher, but they are not as high as you would expect. And this can be very helpful when taking out monitoring campaigns, because you will still wonder, why are my measurements so low or so high? So the assumptions that we make in Greater and the model that we run can help to identify hotspots not only, but also to explain concentrations. And if you like to know more about this, there are 2 papers out, where one is under revision and the other one is in preparation, where the first one is focusing on the new model version that we have, the application of Greater 4.1, and the other one is about the talk that I give today, so the modeling of micropollutants in this strongly regulated cross-border catchment. Yeah, and then I'm just in time or a little bit over, and thanks for your attention.